Let us now take a look at what we have learned earlier and revise it once again for the sake of clarity. So, if you remember that we have talked about inelastic materials and plastic materials, we have not made a great deal of distinction between the two, but there is a subtle difference between inelastic and plastic materials. The inelastic materials do not exhibit a specific trend of deformation as a function of the applied force. So, in fact, they may not deform at all, which I will give an example, or the deformation caused could be partially recoverable or reversible when the load or the force applied is being removed. So, however, the materials which are permanently deformed even when the load is removed are called as plastic materials. Okay. So, what I wish to state is that all plastic materials are inelastic materials, while all inelastic materials are not plastic materials. Let me elaborate this statement a little more. Take an example of a steel rod. Steel is a very well known material and it has been discussed in the context of elasticity quite a bit. The steel rod remains rigid for low to moderate tensile forces. Further increase of the forces shows a linear elastic regime where Hooke's law is valid, which I have told you earlier. While if we increase the force or the load farther, then beyond a certain value the material breaks or the material fractures. So, thus at low or moderate tensile forces, steel behaves like an inelastic material, but this is not plastic. Distinguish it between a plastic material. Now, while at very large forces, when it breaks, it demonstrates a plastic behavior. So, if we summarize this discussion of the distinction between inelastic materials and plastic materials, we could say that the plastic materials are the subsets of the inelastic materials. So, all plastic deformations are inelastic deformations where Hooke's law is not obeyed, but all inelastic deformations again for which the Hooke's law is not obeyed are not plastic deformations. Let me also at the same time revisit the microscopic concept of elasticity, which could actually enhance your knowledge about elasticity and make you understand the notion of elasticity which we have been talking about better. So, from the intermolecular and the interatomic forces perspective, one can understand the elastic behavior. Take the short piece of metallic wire such as a straightened paper clip. You have seen those paper clips. If you just open these windings and straighten it up is what we are talking about as a short wire. So, if you try to stretch it along its length, okay, and if the stretching forces are small, the wire will not break. So, what happens at the atomic level is the following. So, one has slightly increased the average distance r between the atoms which constitute this wire, this metal wire. And however, the attractive forces between the pairs of atoms is able to restore the tensile forces that is given by U. Okay. So, now just do the opposite, that is apply a compressive force or a compressive stress. So, you try to shorten the length of the wire. So, if you do that for short compressive stresses, the repulsive forces between the pairs of atoms combats or it resists the compressive stresses. So, the further observations will reveal that it is fairly difficult to compress a metal, and so that the repulsive force must be really very large, so that one even for small distances between the atoms. Okay. Secondly, once a metal is broken by large tensile stresses or compressive stresses given to them, they cannot be joined together. So, even for a distance as small as a millimeter or even a fraction of a millimeter, the attractive forces are effectively negligible, or they are nearly 0. So, let me now do a dimensional analysis of the Young's modulus to make you understand it better. We go back to this very familiar equation, which is y equal to f by a divided by delta L over L 0. To remind you, you have seen this expression a number of times. Y is the Young's modulus, F is the force or the load that is given to the material in order to cause either stretching or compression. A is the area of cross section of the material, delta L is the change in length, and L 0 is the original length of the material. So, this is truly written as stress over strain. And just to remind you that this stress could be compressive stress or it could be tensile stress. So, in any case, you have the stress, which is the force over area given by mL T minus 2. The reason being that the force is always written as a mass into the acceleration. So, this is mass and this is the acceleration, which is distance divided by time square or velocity divided by time. And A goes as, which is the area of cross section, goes as L square, and the strain is dimensionless. So, I am just simply writing a 1 there. So, the whole thing is actually Newton is the unit for the force and divided by the SI unit for area is meter square. So, Y has the unit Newton per meter square. I shall list out some of the materials which are used in day to day life. Also they are used as construction materials. I will write down their maximum allowable the stresses and the compressive stresses and the shear stresses. So, to begin with, so let us just make this table. So, we have material and then we have tensile strength, Newton per meter square, compressive Newton per meter square, and shear strength again in Newton per meter square. So, iron it's 170 into 10 to the power 6, 550 into 10 to the power 6, 170 into 10 to the power 6, steel 500 into 10 to the power 6, 500 into 10 to the power 6, 250 into 10 to the power 6, brick 10 to the power 6, this is 35 into 10 to the power 6, 4 concrete, which is 2 into 10 to the power 6, 20 into 10 to the power 6, 2 into 10 to the power 6, 200 into 10 to the power 6, 200 into 10 to the power 6, 200 into 10 to the power 6, and we have wood, pine wood, which is 40 into 10 to the power 6, 35 into 10 to the power 6, and 5 into 10 to the power 6. So, these are the maximum allowable stresses for each of these materials. So, we were talking about the strength of materials. I have listed some of the materials which are very familiar to us, and we have seen that if the stress on a certain object is too large, it will cause either permanent damage or it will cause fracture and make the material to break. Some of these materials which are listed on the left are very familiar to all of you. They are used as building materials. They are iron, steel, brick, concrete, aluminum, wood, especially pine wood, and we have listed the maximum tensile strength, maximum compressive strength and maximum shear strength, all in a Newton per meter square. And if one is making a structure with any of these materials such as iron, steel, brick, concrete, aluminum or wood, one should never cross these numbers. And in principle, while making structures, there should be something like 10% of these numbers and should not exceed more than that in any case. So, just to bring to your attention that iron has the tensile strength to be reasonably large, which is 170 into 10 to the power 6, whereas the compressive strength is more than 3 times of that, and the shear strength is again 170 into 10 to the power 6. Similarly, the steel has tensile strengths and compressive strength and shear strengths to be much larger, whereas brick has a small tensile strength and reasonably large compressive strength, and that is why so brick is good under compression, but it is not when it is exerted to tension. And similarly, a concrete also is used for pillars or vertical columns, because the compressive strength, maximum compressive strength is about 20 into 10 to the power 6 Newton per meter square, whereas the tensile strength is small, which is 2 into 10 to the power 6 Newton per meter square. When one uses them in buildings, they use reinforced concretes in which the iron rods are inserted into the concrete structure and which perform much stronger than without them, and it is good for the stability. Here you can see a beam that's been acted upon by a force at the middle, which is like a compressive strength that is given to the beam, and the beam shows a deformation in the middle, and these kind of deformations are to be kept in mind while building structures. So now let us discuss another thing which is very important from the experiment point of view, that is experimental determination of Young's modulus. So here we wish to understand that how experimental determination of Young's modulus for a material of a wire can be determined. So if you look at the picture, there are two wires A and B. A is called a reference wire and B is the experimental wire for which we need to know the Young's modulus. So there is a scale system as a measuring device which consists of a main scale and a vernier scale. Initially both these wires are given some small but finite weight so that they are elongated and straight. Both these wires have same area of cross section and length. So initially the meter reading is noted when the weight in both these wires, the reference wire and the experimental wires, are same, and then the experimental wire is loaded with some more weights which causes an elongation, and again the reading is noted. The difference between the two vernier scales, that is when they are equal weights as compared to when they are unequal weights, are the difference between that is taken as the elongation. So let us assume that the initial radius, the radius of both the wires is equal to R0 and initial length is equal to L0. So elongation due to the weights it's equal to delta L, and suppose mass causing the elongation is equal to m. So the Young's modulus can be written as, so it's mg over pi r0 square. So this is the stress divided by the strain. Okay. So since all these quantities such as m, r0, delta L and L0 all are quantities that we know, using this formula we can find out the Young's modulus of the experimental wire. So now we shall talk about some examples to what we have learned so far, and let us have two plots which depict stress versus strain for two materials, two different materials. And they look like this. So let us call the plots as A and B. So these are stress versus strain characters for two materials, say two wires, and they look like this. The question is that which material has Young's modulus. Second is which of the two is a stronger material. And the answer would be B in both the cases, and let us try to understand why that is the case. The Young's modulus Y is defined as the ratio of stress to strain. So, it is this versus this. Okay. Since B has a steeper slope as compared to A, so B has larger Young's modulus and A has smaller Young's modulus. And to answer the question, second question, that is which one of them denotes a stronger material, again the answer would be B. The reason is that to cause the same strain, you need bigger stress for B. So, to cause a strain of this much, a stress of this is required. However, to cause a strain of again the same amount, a much larger stress is required. So, strength, this B material has more strength as compared to the A material. So, here in the next example, let us compute the bulk modulus of water from the data that is given. So, the initial volume of water is given as 100 liters. The pressure increase is given by delta P, which is equal to 100 atmospheres. And just to let you know that 1 atmosphere is equal to 1.013 into 10 to the power 5 pascals, and 1 pascal is equal to 1 Newton per meter square. So, if you need to calculate the bulk modulus from this data, so bulk modulus is given by your delta P divided by delta V divided by Vi, and delta V is Vf minus Vi, which is equal to 0.5 liter. So, if you put in all these things, which are 100 atmosphere, which is equal to this pascals, and into 100 liters divided by 0.5 liters, then this thing comes out to be equal to 2.026 into 10 to the power 9 pascals, which is equal to 2.026 into 10 to the power 9 meter per Newton per meter square. So, the question is that why do water, so water seem to be having a large bulk modulus. In fact, the gases have more bulk modulus because they are compressible. So, more the compressible the fluid is, more bulk modulus it will have. So, the bulk modulus from the data is given by delta V over Vi, which is equal to delta P into Vi divided by delta V, and this is 100 atmosphere, 1.013 into 10 to the power 9 10 to the power 5 pascals into 100 liters divided by 0.05 liter. So, this will come in pascals, and which is equal to 2.026 into 10 to the power 9 pascals, which is equal to 2.026 into 10 to the power 9 Newton per meter square. So, this is the bulk modulus of water for a pressure given to be of 100 atmosphere when the liquid has expanded from 100 liters to 100.5 liters. So, as a third example, let us see again the computation of bulk modulus, now not for a liquid, but for a solid copper cube, which is 10 centimeters of age, and it is subjected to a pressure, hydraulic pressure of 7.0 into 10 to the power 6 Pascal, and given that the bulk modulus of copper, solid copper, is 140 into 10 to the power 9 Newton per meter square. So, we again use this formula as delta P divided by delta V over Vi. Do not forget to convert your VIs, which are in 10 centimeters whole cube, or this is equal to 0.1 meter whole cube, which is equal to 0.001 meter cube, and your delta V is what is wanted. So, delta V divided by Vi becomes equal to a delta P divided by B, and this Vi can go upstairs for you to compute delta V, which is a change in volume of the solid copper cube, and this can be when you put in all these values, delta P is 7 into 10 to the power 6 pascals. This is 140 into 10 to the power 9 Newton per meter square, and this is equal to 0.001 meter cube, and this is almost equal to 0.5 into 10 to the power minus 6 meter cube. So, that is the change in volume that you will have for a solid copper cube when it is subjected to a hydraulic pressure of 7 into 10 to the power 6 pascals. So, let me write down a problem. So, there are two wires each of diameter 0.25 centimeter, one made of steel and the other of brass, as shown below. I will just show the diagram in a moment. The unloaded length of the steel wire is 1.5 meter, and that of the brass wire is 1 meter. Compute the elongations of the steel and brass wires. Given Y steel equal to 20 into 10 to the power 10 Newton per meter square, and brass 9 into 10 to the power 10 Newton per meter square. So, the diagram is the loads that are these are subjected to is steel. The steel wire is subjected to a load of 4 kgs and the brass wire is subjected to a load of 6 kgs, and you need to calculate the elongations of the steel and the brass wires. So, let us do this problem. So, there is a rigid support here, there is a steel rod which is loaded with a weight 4 kg. So, this is steel and this is 1.5 meter long, there is a 1 meter long brass wire which is loaded with a 6 kg. This is brass and this is 1 meter. The diameter of both are 0.25 centimeter, which is equal to 25 into 10 to the power minus 4 meter. Y of steel is equal to 20 into 10 to the power 10 Newton per meter square. Y for brass to be 9 into 10 to the power 9 Newton per meter square. So, we shall use this formula which is well known to us. It is stress divided by the strain, which is this. So, the extensions are going to be computed as F into L 0 divided by A into Y, and hence for steel. So, the extension in steel, let us call it delta L steel, that is going to be now there are two weights acting on the steel wire, which is 4 kg and 6 kg, assuming the wires are massless. So, you have 10 kg of weight being supported by the steel wire. So, this will be like 10 kg and taken G to be taken as 10 meters per second square, it will be 100 Newton and 1.5 meter is the length divided by pi into 25 square into 10 to the power minus 8 into 4 and the y to be given as 20 into 10 to the power 10 and this will be in meter. If you do this simplification, this comes out to be 1 into 10 to the power minus 4 meter, whereas the same thing done for the brass, we have a delta L brass and now the weight that the brass wire supports is 6 kg. So, it will be 60 Newton into 1 divided by pi and 25 square 10 to the power minus 8 into 4. Now, the brass has a Young's modulus which is 9 into 10 to the power 9. I am sorry, this is 9 into 10 to the power 10. So, this will be 9 into 10 to the power 10, and if you simplify this, this comes out to be 1.35 into 10 to the power minus 4 meter. Thus, the brass wire has a little more expansion than the steel wire. The steel wire, even though it is loaded with a larger weight, it still is it is more difficult to cause elongation in the steel wire as compared to the brass wire. Let us do a problem on Young's modulus, elastic properties of matter. Now, let us talk about a titanium alloy. So, a cylindrical specimen of a titanium alloy having an elastic modulus of 108 gigapascal. As we have told you many times that the elastic modulus or the Young's modulus in practical units is represented by this Pascal or gigapascal, whereas we know that 1 Pascal equal to 1 Newton per meter square. So, this and an original diameter of 3.9 millimeter will experience only elastic deformation when a tensile load (2000 Newton) is applied. Compute the maximum length of the specimen before deformation. If the maximum allowable elongation is 0.42 millimeter. So, titanium alloy is given, the elastic modulus or the Young's modulus, which means the same thing in this case, is given and also the original diameter is given. It is experiencing only an elastic deformation, which means we are fully in the elastic limit, when a tensile load of 2000 Newton is applied. So, compute the maximum length of the specimen before it starts deforming, and it is given that the maximum elongation is 0.42 millimeter. Okay. So, to solve this, the initial area of the cylinder is A0 pi d0 by 2 square, where d0 is the initial diameter, which is given as 3.9 millimeter. So, d0 equal to 3.9 millimeter. So, now the original length is related to the deformation. Let us call this original length to be say L0, which is related to the deformation by this simple formula, where delta L is the elongation, which is given, the maximum elongation is given, the Young's modulus or the elastic modulus is given, and the tensile load is given to be 2000 Newton, A0 is given. So, now we can put everything here and calculate. So, this is my elongation, this is my Young's modulus, then there is a pi, and then there is a 3.9 into 10 to the power minus 3, there is a square there divided by 4 into 2000 Newton. So, this 4 is coming because there is a d0 square by 4, and if you calculate that, this becomes 0.257 meters, which is equal to 257 millimeter. So, this is the maximum length of the specimen before it starts deforming. So, having understood a number of things about elasticity so far, and also that we have discussed plastic behavior and plasticity and the difference therein with inelastic materials. Let us now look at certain quantities or rather certain terms which are of importance not only in the context of physics or the mechanical properties of solids, but in the context of your daily life or even in the context of chemistry that you would see, and which are also about the properties of matter, and we have not discussed them very explicitly. A number of things such as, let us just list them out. One, it is called as toughness. 2, it is brittleness. 3, it is hardness. 4, say for example, resilience, and maybe 5 as stiffness. You may have heard these terms that appear on the board in the context of something else and also in the context of properties of matter. Let us now try to give a formal definition to it, so that you understand it better. and what they have got to do with the modulus of elasticity and so on. Okay. So, let us just talk about start with this toughness that we have written it there, and let us define toughness. So, it is the ability of a material to absorb energy and plastically deform without rupturing. So, here it goes, it is the ability, toughness is the ability of a solid material to absorb energy and deform in an inelastic or a plastic manner without breaking apart or without rupturing. So, it is actually the amount of energy per unit volume that a material can be subjected to before it ruptures or before it breaks apart. The examples can be given in the following fashion, that you see materials like ceramics which have small toughness, which means that they actually break apart when they are subjected to a tensile or a compressive stress. So, even then they are very strong materials. So, the ceramics are actually strong materials where they are low on toughness, whereas rubber is actually a tough material, but it is weak in terms of its strength. Okay. So, we give examples of ceramics as having low toughness, whereas rubber to be having a high toughness. Let us go to this second quantity called as brittleness. So, this you may have heard of when you have talked about materials in chemistry. So, a material is called as brittle when it breaks when it is subjected to a stress, and so without undergoing any kind of significant deformation. So, it just breaks. So, it breaks being subjected to stress without undergoing significant deformation under strain. So, technically speaking, they absorb a very small amount of energy prior to fracture and even when they have very high strengths. So, ceramics and glasses, for example, they do not deform plastically and they actually break very easily under stress. So, they are known as brittle materials. In fact, some of the polymers such as polystyrene, they are also known as brittle materials, and even steel, which is known to be quite tough, at very low temperatures can become a brittle material. Similarly, if you have gone to these shows where they show the utility and various things with liquid nitrogen, you might have seen that they actually dip their hands inside the jar containing liquid nitrogen, but they wear sort of gloves in order to put their hands in, and the reason is that the bones become extremely brittle at that temperature. The liquid nitrogen temperature, which is actually the boiling point of nitrogen, is about 77 Kelvin. So, it is not advisable to touch liquid nitrogen by bare hand. Let us talk about the third quantity, which we have listed down, such as hardness. So, hardness is the measure of how resistant a solid is to a permanent shape change when an applied force is given. So, there are different kind of hardnesses such as scratch hardness, indentation hardness, etc. So, it is the property which says that or rather it is a measure of how resistant a material is to a permanent shape change when subjected to an applied force. So, glass materials have a lot of hardness as compared to soft materials such as copper or aluminum. So, let us look at the next property called as resilience. So, it is the capacity of the material to absorb energy when it is elastically deformed, and then when the inner energy is released upon unloading. Okay. So, resilience is the capacity of a material to absorb energy when it is deformed elastically and then the energy which it has absorbed is released upon unloading. So, once it absorbs energy when it is loaded, and after that when it is unloaded, that is the load is taken off, then it releases energy, and it is obtained from the area of the stress versus strain graph. So, let us take a typical stress versus strain graph. So, till this is the elastic limit. So, let us call this strain as delta x elastic, and this is the stress which is equal to F over A. Let us just denote it by sigma. So, the area under this curve till the elastic limit is called as the resilience. So, what is so the energy that is absorbed and hence released upon unloading is given by sigma, which is the stress, and a dx from 0 to delta x elastic. And now, because this will give the area of this. So, this is my value of sigma here. So, this has to be taken half of it, because we are only talking about the area of a triangle and not the area of the whole rectangle that appears here. So, this is equal to half F over A and a dx from 0 to delta x elastic, which is equal to half F by A into delta x elastic. So, that is the U resilience. So, this is the energy stored and hence released upon unloading, for which measures the resilience of a given body. Now, let us look at the last one, which is the toughness, rather stiffness. Sorry, not toughness, it is stiffness. Toughness we have already talked about, which is what we have begun our discussion with. So, stiffness is defined as the ratio of the steady force acting on an elastic body to the resulting displacement. So, it is the ratio of the force that is applied to the body and the displacement that occurs due to the applied force. So, as such, a stiffer material has a higher stiffness, has a higher elastic modulus, I am sorry, elastic modulus. So, stiffness is a measure of or rather the elastic modulus is a measure of stiffness. The higher the elastic modulus, higher is the stiffness. So, having learnt about the elastic properties of matter, we shall consider now the effects of temperature, which we have missed out so far. And as we know that temperature plays a very important role in everyday life, so it will play also an important role while discussing the elastic properties of matter. So, because of temperature, the stress that is developed, it is called as a thermal stress. And so, we shall discuss thermal stress in next day's class, and we shall also talk about the elasticity of different components of human body and how they are different than the solids that we have discussed so far.